So I'm going to do some things at the beginning of class that may answer some of the questions on the web work. I noticed 2 or 3 that have slightly lower success rate. So these couple of things I'm going to do at the beginning of class may address those questions. But so let's look at this slide that I had before. This one, okay. So this is what we were talking about directional derivative before, okay? And we said that directional derivative is about kind of like a weighting between the two. Our partial derivatives kind of are the 2 baseline derivatives from which all the other directions we can get. And we said that we can do that by putting cosine theta, that amount of weight, onto the partial with respect to x, and sine theta, that amount of weight, onto the partial with respect to y. And then when we're pointing in the direction of x, we'll get all this, right? Because that theta will be 0, and cosine will be 1, and etc. And so then we said, oh, well, that's like the dot product of this thing we called the gradient vector, and cosine theta, sine theta, which is what? A unit vector in the direction we're interested in. So cosine theta, sine theta is the unit vector in the xy plane. That's our initial direction that we want to find the rate of change of z. Okay, and so we said this is gradient dot u. And then we said we don't really need theta, right? We could be given a direction by a vector. Well, then what do we need? We need the unit vector in that direction that we're specifying, right? We just need the unit vector. We don't necessarily have to know that trig angle theta. And then we said since it is the dot product, we could write it this different way. We could write it as the product of the magnitudes times cosine of alpha, where we said alpha was the angle between the gradient and our chosen direction. So alpha is not theta. Theta is the standard trig angle, swept counterclockwise from the x-axis. Alpha now would be the angle between our chosen direction and whatever direction the gradient points in. Well, that's just 1, so we end up with this. And this form of the directional derivative, then, in fact, this is the magnitude. Yeah, so yeah, this form of the directional derivative then is allows us to find the direction of max ascent and the value of max ascent, and it's based on the angle alpha between our unit vector, the direction we're choosing, and the direction of the gradient, which is fixed, right? For any given function and point on that function, you've got the gradient as a fixed vector. Okay, so let's just make a little chart here. We want max directional derivative. We can talk about min. We can talk about 0 directional derivative. I want to do this one. Okay, and so if we want to maximize this, we said we want cosine alpha to be what? The biggest cosine alpha could be is 1. Okay. Which means that alpha is 0. And what was alpha again? Alpha is the angle between our chosen direction and the vector, the gradient. And if that alpha is 0, then what do we choose to be the direction? The direction of the gradient, right? So we do direction. And then we'll say rate of change. So what's the direction? Direction is direction of the gradient. And then what rate of change do we get when we do that? When cosine of alpha is 1, the value of the directional derivative is magnitude of the gradient. So you see it's really kind of all about the gradient here. The gradient is a vector. It has a direction. That will be the direction of steepest ascent or greatest rate of change of all 2 pi directions we could choose. And then the magnitude of that will be magnitude of the gradient. That's the rate of change. So that's the biggest rate of change we can get. So one thing we didn't talk about, but it's not a big stretch, somewhat obvious. We want the minimum rate of change, which we cosine alpha is -1, right? -1. And so then in order for cosine alpha to be -1, alpha is what angle? Cool people use radians. So yeah, so pi, right? So if we want -1, so this is what? The greatest negative rate of change. The greatest negative rate of change is going to be, what direction will that be? So the opposite direction of the gradient, right? So, and it makes sense. If you're standing on the side of a hill and you're looking at the direction of steepest ascent, where's going to be your direction of steepest descent? Exactly behind that direction, right? Should make perfect sense. And it comes out in the math too. So the direction is going to be the opposite. And then what's going to be the rate of change? Yeah, so it's going to be the opposite of, it's going to be that. Now we want 0. We want 0 rate of change. Cosine is 0, and alpha is pi over 2, or negative pi over 2, or 3 pi over 2. There's 2, right? There's going to be 2 directions. And these are going to be, how are these going to be situated compared to the max and the min? Right, orthogonal, because pi over 2 is orthogonal to both 0 and pi, so is 3 pi over 2. So the direction is going to be orthogonal to the gradient. And orthogonal to the gradient means how compared to the contour lines. Contour lines are parallel, right? And this tangent to or parallel to contour lines, because contour lines are where z stays the same, and that's what we're saying. Rate of change is 0. Rate of change is 0. Z is going to stay the same, so you're going to be going along or parallel to the contour lines. So let's see that in action, that little table in action. Everyone got it? Can I go on? Can I take this off? So, just looking at on the left there. So about where are we going to have steepest ascent, right? Like, we got this paraboloid. It would be like, which direction will we, if we're on the side of a mountain here, which direction will we go to go up the most steeply? Something like the origin. Now, is it exactly toward the origin? Probably not. But something over here, like this. Okay? And we found that by, what direction is that? So this is our direction right here, back down here. What direction is that? How do we get that vector? It's the direction of the gradient. It's the direction of the gradient. So you could unitize that. You can take the gradient and unitize it, meaning make it 1, or just leave it like it is if they both have the same direction. But that's the direction of the gradient. And so that's, in fact, right there. So I'm going to show you the gradient is That's the direction of the gradient right there, and I'll put it right on there. And now look over to the contour line, and here's also our mini unit circle, right? This is our mini unit circle at the point in question, 2, 2. And notice how the direction of that compared to the contour line. What is it? Do you see that it's orthogonal, right? So the direction of steepest ascent is orthogonal to the contour line. And so now this is the steepest way up. And then we said, what about direction of steepest descent? It's going to be exactly pi from that. Also orthogonal to the contour lines. But now heading down in the steepest way, or with the largest negative rate of change. Okay, and then direction of 0 would be along the contour line. So now we're talking about derivative right now, so the fact that it's deviating now from the contour line far away, that's okay. What we care about is for a small change in our direction that we pick, do you essentially, for a very small change, walk along the contour line? So really want that vector to be tangent to the contour line. And we've got two ways to do that, right? You can walk around the mountain this way and stay at the same level, or you can walk around the mountain this way and stay at the same level. And so we see it there on the right. Okay, questions on that? Yeah?
What if there's two mountains beside each other? That's so how would you, wouldn't there not be a descent then? And
But
it'd just be two ascents, and they'd be.
But we're talking about at a particular point. Okay. So it's a little bit misleading maybe to think about this thing globally. I keep talking about a mountain. Everything I'm talking about in terms of rate of change is just in the tiny little local area around this point. So does that answer the question? So if you have two mountains, you're talking about a whole set of points. So at any one given point, you're going to have only one direction of max ascent and min ascent and 0. Does that make sense? Yeah. So really, when we talk about derivative, we're just talking about a teeny little neighborhood around each point in question. And there's always going to be a direction of the gradient, which will be max ascent. Max negative ascent is opposite that, and then the 2. So yeah, you don't. So yeah, I'm using this mountain analogy, but that's a little bit misleading because we really want everything in the mathematics is really talking about that teeny little neighborhood around a given point. Yes, sir.
Will we ever get to the point where we find the point on the surface of maximum ascent or descent, like the point of that?
You're talking about the maximum, like local maximum?
Just like in general, the maximum of the whole.
Yeah, we'll start that today. So now you're talking about actual maximum and minimum values on the surface. Is that what you mean? Yes. So yeah. So and then that leads me to what I want to talk about next. Here's another one. So here's this surface. I'm only showing it for x less than 0, so behind the yz plane. Okay, so one of these sets of contour lines is showing maximum and one showing minimum. So which one is the one up here? So we have like either a hilltop or a valley here. Is this our hilltop here, or is this our valley over here? What is this? So remember, we got to get our orientation right. Where's the first quadrant? The first quadrant is here, right? So this over here is which quadrant? Second. So this is hilltop, right? This is this hilltop. This right here is showing this hilltop right here. And then we move into the third quadrant, and we have a minimum there, which is this is the third quadrant, right? So remember, positive y, positive x means you got to think about standing over there and looking down on your xy plane from the left, down that way, and then you get the same thing here. But anyway, if we were right here, and say we wanted to walk to the apex in the shortest route possible. Do I draw a straight line from there to there? Is that how I'm going to get to there at the shortest route possible? Seems like it, right? Seems like the shortest distance between 2 points is the line, right? But it's not right. How will we get there the fastest? How are you going to get to the top of a mountain the fastest? Yeah, so you always want to go in the direction of steepest descent. That's going to get you there the fastest. Even though this appears as a curve, there's a dimension missing here, right? The z dimension is missing here. So what I'm going to do is I'm going to start going this way. Not this way, right? I'm going to go this way. And then I'm always going to, like he said, always stay orthogonal to the contour lines. How am I doing? That was a little too low there. Something like that. So it's going to be more curved. In the plane in the bird's eye view, it's going to look like a curve, but that's actually the straightest, the most direct route to the top. Is always walking the steepest path, which is perpendicular to the contour lines. Okay, maybe the least enjoyable too. But if you want the shortest route up, you walk the steepest route, and that means always perpendicular to the contour line. So in this case, it makes kind of curve instead of what would be more like a straight line like this. Okay, and then the question is, where is this point? So that's the question you're asking, right, Ezra? Yeah, and we'll get to that later today. So the idea of a local maximum or a local minimum of a surface, that's important, and we'll talk about that. Okay, so then if we think about, yeah.
So would the shortest line, like the shortest distance and like the fastest necessarily be the same?
Why?
Like,
You're thinking about time?
right.
I mean, you're bringing time into it?
Yeah. So just because it's like the fastest route, does that make it the shortest as well, or is it just?
Yeah. So what you don't see here, the reason that it's curved, but you don't see the fact that if you walked in what looks like a straight line here, that would also be curved because of the z coordinate. You're not walking in a straight line. You're actually kind of wrapping around the mountain also. But so in terms of shortest distance, and then would also be shortest time, you're going to choose the path that's... It's kind of like great circle, right? Like if you're looking at the globe and you look at flight patterns, what would look like the shortest flight pattern is not, right? It's like the greatest... Right, yeah. Following the great circle is a shorter distance, even though if you're looking at on a plane, it looks further. Same kind of idea. Yeah, sure. Other questions? Okay, so let's go back to this one, or anyone. Turn this off. Now I want to just have you guys think about us for a second here. Let's just throw this right there. A little bit. No, not there. Good. Okay. So suppose we have this direction right here. So there's some different things. There's the rate of change of z, which is our directional derivative. Okay. Then there's this vector. right? So this vector is a vector. So rate of change is a value. This vector, do you see? Those are highly related things, right? What the rate of change of going this direction on this surface, and this vector, which is pointing, pointing, it's the tangent to the surface and pointing up in the direction of that rate of change. And then there's also the angle of ascent, or angle. And so these three things are highly related, right? But they're all different. They're all different things, different mathematical entities. Highly related, but different. And so I think it'd be nice to kind of define each one and maybe come up with some relationships between them. So what are each of those? How are they different? So think about them individually. How are they different? And then how are they related? So maybe can we take a couple minutes to you guys just brainstorm on that? Because you may be asked for the rate of change in this direction. You may be asked for a vector pointing in the direction along the tangent of the tangent to the surface that kind of depicts that rate of change. Or you, like in the web work, the last question asks for the angle of ascent or the angle above horizontal. Highly related, but all different. So why don't you talk that out a little bit, and then we'll discuss together. Ready? Go. Everyone's talking to somebody. Call the rate of change m, the directional derivative. Call that m. Call the vector ABC, the one I'm showing, and then the angle of ascent beta. Okay? What's the relation? What's the meaning of each, and what's the relationship between m, a, b, and c, and beta? Can you come up with some mathematical relationships too? Okay, keep going. This is u. That's not the vector I'm talking about. I'm talking about the vector tangent to the surface that's depicting this rate of change in that direction. A three-dimensional vector. Direction vector u, but then we have a vector that we can think of as in the direction of u, but tangent to the surface, showing the rate of change, right? And so we'll call that just vector, just generically ABC. And really, any constant multiple of ABC is valid for ABC. Does that make sense? So, and then we have beta. What is beta? So beta then would be that angle right there. Angle of ascent is the angle beta. So, what did you come up with? Volunteer. Just one thing that you talked about that you came up with. Seth. Okay, so yeah, so what is this vector that's kind of like the dotted line there? But related to ABC, it would be what? That vector, not necessarily unit. A, good, AB0, okay? So beta, what, is the angle between ABC and AB0, right? And I made it too big, but think about that vector right there. What's that vector right there? 0, 0, C, right? 0, 0, C. So it has magnitude C. My drawing's getting really bad. That has magnitude C, and this one has magnitude of what? Square root of A squared plus B squared, right? So what would that angle beta equal? It's not cosine. It's going to be tangent, right? Because it's going to be opposite over adjacent. So beta is going to be what? Tangent inverse of c over square root of a squared plus b squared. Did anyone get that before I wrote it? Does it make sense? All right, what about the directional derivative? What does that equal? So that's the rate of change, and rate of change is defined as? Rate of change is defined as? Just in general, it's the change in, no, not x. Change in z per change, that's directional derivative now, per change in so what? Per change in the direction of u. So I think I used du vector last time. That's probably really bad notation, but it's the idea that counts, right? So in the direction of u, a little change, and then what du tells us that then the change in z will be the directional derivative times whatever change in the direction of u that you took. All right, so what is that in terms of the other stuff? What is the change in z here in terms of other stuff? So in terms of beta or a, b, and c? C over the amount of change in the direction of u. This isn't one. This is some change in the direction of u is what I'm meaning by this. So what will that be? Yep. So it's the ratio. It's the change in z, which would also always be in the ratio of c to square root of a squared plus b squared. And what about the relationship between the directional derivative and beta? So what would that be in terms of beta? Tangent or inverse tangent? Tangent gives you opposite over hypotenuse, so it'll be just tangent of beta. So maybe these are formulas you're not going to use very often, but I'm just trying to give you some structure in your mind when you come upon it. When you have this vector that's pointing in the direction, okay, how does that relate to the rate of change? Because they're so similar, but this is a vector and this is a number, right? Same with beta, right? Okay, so I hope that helps a little bit, just thinking about different ways that you can talk about rate of change at a point on a surface. You can talk about the value of rate of change. You could talk about it as a vector. You could talk about angle of ascent. Okay, any questions on that? So let's go back to our question of, coming back here. So now, I want to write the easiest vector I can for the direction of x. What's the easiest vector I can? And this relates to our question last time of do you have a question or are you answering the question? You have a question, okay? Yeah, it's not about finding values, right? So all I'm saying is that in the direction of u, at the point, if you took a vector tangent that's like pointing in the direction and encompassing the rate of change that we're talking about. it could be any scalar multiple of that. It could be really small. I could have made it this large, this. I could have made it this long, or it could be as long as what's showing in the animation. And all those relationships still hold. So there is no finding A, B, and C. You know what I mean? Like unless you had a context. So, yeah, I mean, I guess I know what you're saying. Like if you had the rate of change, then right. So if you had the rate of change, then could you come up with a particular vector that would match that? So you would need the direction, you need the u vector, and you need the rate of change, and you should be able to come up with that vector, right? So if you were in the direction of, what is this? -2, 1, and duf were 1/5, could you come up with a vector, a tangent vector like we were talking about? Could you do that? And you should be able to, right? So you're going to find the magnitude in this direction, and then you want z, the change in z to be 1/5 of whatever magnitude you have in the xy direction, because that's what rate of change means. This rate of change means, given a change in this direction, the change in z will be 1/5 times that change. So what is the magnitude if we're just going to use those? That's not actually u, so it's not unit, but you got the idea. So what is the magnitude of that? Square root of 5. So if I went a distance of square root of 5, how much would z change according to this? Square root of 5 over 5. So therefore, -2, 1, square root of 5 over 5 would be one possible ABC. Make sense? Okay, so now we're going to go back to the direction of x. And I want the easiest version of, quote, ABC in order to find the equation of that tangent line, right? So last time I asked you to find this equation of that line, okay, the equation of that line. And what do you need? You're going to need the point, already got it, 2, 2, 1, and the direction vector, right? Direction vector, a vector parallel to the line. So what would be the easiest direction vector, the most simplest direction vector you could come up with for this? One thing we know right off the bat. What do we know right off the bat? What's that? He wants y is 0. Agree with that? For this vector? For that vector that's tangent to the curve solely in the x direction. Right, because the y component will be 0 because there's no change in y. And now here's this question that I kind of, what is the rate of change in that direction? What is the rate of change? Stop it. A little better place here. So what's the rate of change, Mark, first of all? What's that? Right. So the partial of f with respect to x is the rate of change of that. And so we need to pick an x component and a y component to give us that rate of change. That gives us the rate of change, f of x, the easiest pair of values that do that. He's suggesting that make a change of x of 1, and then the change in z would be partial with respect to x. So some of you, I hear some of you getting it, right? So if that were 1 and that were the partial with respect to x, that would be that vector I'm showing you. Why? Because given a change in x of 1, how much does z change? partial derivative times the change I picked, 1. And there it is, f of x. You see that? Or partial with respect to x. Make sure this makes sense. If it doesn't, ask. Right? Because what do we know? In the x direction, dz equals the partial of x, say at our point, times dx. Given any change in x, the change in z is the partial derivative times the change in x. So make your change in x as easy as possible. Make it 1. And then what's your change in z? 1 times the partial with respect to x, which is the partial with respect to x. So there's your change in z.
So your z value would be an equation in this instance, because we're not given a point, unless whatever the point is.
Right. So if we have, yes. So in order to have a value, we need to have the function be defined, and we'd be at a particular point, and then that's a value. Right. But if it's, if the function's defined and we're saying we want this for any given point, then that f of x is actually a function of x and y, where you are. Yeah. Okay, cool. And so then what about this vector? Okay, your turn. So I want that vector. This is in the direction of y. I want that vector, which would help us find the tangent line in the y direction to the surface, right? The tangent line to the... Okay, what doesn't change? X doesn't change. And so now we know we have the relationship that the change in z is given any change in x, the change in z is the rate of change times the change, given any change in y. Given any change in y, the change in z is the rate of change times the change in y. Therefore, we can use 0, 1, fy. So now I want you to write 3 things. I want you to write the equations of each of these 2 lines. Now it should be pretty smooth sailing from here. And then I want you to write the equation of the tangent plane. Get nice and light. Does that show up pretty good? No, who remembers their planes? So, when those 2 lines, the tangent plane is pretty easy if you remember the relationships, the vector relationships, right? If you remember the vector relationships with planes, then it's you're 1 step away to writing the equation of the plane. So write the equation of each line, and then see how you do to write the equation of the tangent plane. Tangent plane. Go. 5 minutes. So, the point is 2, 2, 1. The point is 2, 2, 1. This, in the x direction, we got the direction vector 1, 0, partial with respect to x. In the y direction, we have the vector 0, 1, partial with respect to y. Yeah, sorry. It's the same one from last time. So it's f of xy equals 4 minus x squared over 2 minus y squared over 4. Is that what we did last time? Okay. And then we found that this direction vector was 0, 1, partial with respect to y. This direction vector is 1, 0, partial with respect to x. This point is 2, 2, 1. I think that's everything you need. Okay, the line, you should have the lines done. I got the lines up there. Compare your lines. Remember, point plus your parameter t times the direction. For the particular point 2, 2, 1, the partial with respect to x is -2, and the partial with respect to y is -1 at the point 2, 2, 1. Questions on the lines? Remember doing that? Remember doing lines in space? And I also put the parametric version of line 1, right? X equals 2 plus t, y equals 2 plus 0 t, z equals 1 plus -2t. Questions on the lines? Okay, how are we going to get the plane? What do we need to write the equation of a plane? Point. So we need a point, right? Which we got, right? That's easy. 2, 2, 1. And what else do we need? What's A, B, C? Normal, right? A, B, C in an equation of a line is how related to the line? A, B, C, that vector A, B, C, how does that vector relate to the line? For a line. A, B, C in a line. A, B, C in a line. How does that relate to the line, that vector? What do you mean? If it's the direction, then how does it relate to the line? It's not orthogonal. It's not. That's why I'm asking the question. Parallel, right? It's in the direction of the line, which means the vector is parallel to the line, or you could place it right in the line. Vectors are mobile, right? Vectors are mobile, so parallel to the line, or you could just take that vector and stick it right in the line. What about ABC for a plane? Different ABCs, not parallel. There's an infinite number of parallel vectors to a plane, but to orient the plane, we need the normal vector, right? The normal vector will orient the plane. So how are we going to get the normal vector here? You can cross product these two vectors they're parallel to each line. Okay, now I'm going to do that for this problem. I'm going to do that in the generic case, right? So this would be true now for any, if I cross product those, won't I get the normal vector for any function at any point? And it'll be normal to the surface. Do you see that? Because this is generic for any, this is generic for any function f at any point. So let's do it generically. So how to do the cross product? I'm going to do I, J, K. Remember, it's the determinant of the matrix. So 1, 0, partial with respect to x. 0, 1, partial with respect to y. I'll do the determinant of that. And the way I like to do that is to write the first two columns again. And then do my diagonals. 3 down to the right, add. 3 down to the left, add. So I component, negative partial with respect to x. Agree? J component, 0 this way, negative partial with respect to y. Finally, K component, positive 1 and 0. So important vector. Why? What is that vector relative to the surface? So forgetting about our plane, just now that vector relative to the surface at the point on the surface. Normal to, this is the normal vector, or a normal vector to f. now you can write down the equation of the plane, right? What is our opposite of our partial with respect to x will be? What value will that be? Positive 2, right? The opposite of our partial with respect to y at that point? 1. So now you got your orthogonal vector. 2, 1, 1. And then you just put everything in, and you get the equation of the plane I showed you. Okay, so the equation of the tangent plane then is? What'd you get in the final analysis there? 2x plus y plus z equals 7. Someone else get that? All right, very good. Okay, so now this, so let's just write it generically then. Can I erase everything I've written on the screen? Okay, so equation of the tangent plane. Then is the opposite at, so 2f at a, b, f of ab. Going to be negative partial with respect to x, ab, times, see if I have room, x minus a minus partial with respect to y, ab, times 1 minus b, plus, am I going to make it? Z, so 1 times, right? That was 1 times z minus f of ab equals, I made it. Does that agree with what we found? I'm plugging in the generic normal vector, opposite of partial with respect to x, opposite partial with respect to y, and 1, right? There's a 1 there. That's our normal vector to the surface at the point a, b, and then the function value, the z value at ab. That would be 0. If I rearrange this, I get what's called the linearization of the plane, or of the surface around that point. So I'm going to solve for z, and I'm going to call that L at AB. So all I'm doing is solving for z. This is easy. I'm just going to add the first term, add the second term, and then after that I'm going to add f of AB. So it's just basically the whole same thing, just written in a different form. F of x AB times x minus a plus f of y AB times y minus b. Just added that whole thing. I just added that whole thing, and I'm going to add that right there, and I got it. So this is called the linearization of f at point B. It's like the twin brother of the tangent plane, because it is. I mean, it's the equation of the tangent plane, but solved for z. And what are we going to do? We're going to use that to estimate values of z close to AB, f of AB, because it's tangent plane. So this is called the linearization of f at AB. And again, what's the use of that? It will estimate values of z close to a b f of ab. And that should make sense, right? If you're close to that point of tangency, really close, it's in some small neighborhood around, some circular neighborhood around AB, that the tangent plane and the surface are going to be very, very close, especially if your neighborhood is very, very small, right? The smaller that you make the possible values close to AB, the more that the linearization, the tangent plane is going to essentially be the exact same as the values of z of the surface. Okay, but you get too far away from a comma b, and you see that the plane deviates from the surface, right? So equation of the tangent plane is like, in Calc 1, it's like the equation of the tangent line to a curve. And we know that really close to the point of tangency, the line and the curve are essentially have the same function values. It's the same thing here, it's just we have another dimension coming into it. So this is for estimating values of z on f when x comma y is close to AB. Okay, does that make sense? So then, if I'm at AB and I make a little, I change my x comma y a little bit. So here I am at, where's it light? There we go. Still see it? Good. Okay. So here I am at A comma B, right? Right there at that point in question. And I'm going to just change a little bit. Just a little bitty change. A small change away from AB. How could we approximate how much z changes when we did that? So now I want to get just a rough estimate of how much did z change when I was sitting at AB and I moved a little bit away in any direction. I moved a little bit away from AB, and I want to get a quick and dirty estimate of how much z changed. So I'm asking for what? Asking for how much z changed for a little small change. I'm asking for what, first of all? What is that called? I'm going to change my location away from AB just a little bit in any direction. And I want to know how much does the value of z change. So I'm asking for what mathematical thing? I heard blah, 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 blah. And so those who said dz, congratulations. Did you say, so some of you said dz. That's what I'm asking for. I'm asking, what is dz? Well, what was our basic construct for this? What was our basic construct for dz? dz will always be what? The change in the dependent variable will always be rate times the change that you initiate, right? It's going to be whatever your rate change. But I really have what? When I do that, I have a little change in x and a little change in y. So I'm going to get some change in z due to the change in x. What's that? How much change do I get due to the change in x? Right. Given any change in x, the change in z is be the partial of x, so AB, But when I moved away from that point, I also had a change in y. How much contribution to dz did I get from the change in y? That's a really, really poorly. I'll write that again. All right, given any change in x, the change in z will be the rate of change in the direction of x times the change in x that we picked. But I'm also going to get a contribution to dz from y. Given any change in y, how much does z change according to that change in y? Fy dy. So, and then sometimes in math, things are as easy as you'd hope they would be. What's the total change in z due to the change in x and the change in y? Get to add them together. Yes. Right? So I'm going to, which it makes sense though, right? Because if that's my little change, then I had a little change in x this way, and I'm going to get change in z for that. And that's not going to be, because it's orthogonal to y, there's going to be no overlap in these two, right? There's going to be no influence from y on that part of the change in z in the direction of the change in x. And the same thing with the change in y. In the direction of y, there'll be no influence from the change in x. That's why we can just split, they're orthogonal. X and y are orthogonal. We can just add them together. So this is called the differential in z, the differential in z. Is it the true change in z? Is it the true change in z? I have a no. Is it the true change in z on the gold surface? Does this calculate the true change in z? I have a no. Anyone say yes? Yes. Yes. Anyone say it depends? What does it depend on? Alexis. Right. If you choose dx and dy small enough, you won't be able to tell the difference between this estimated change and the real change in the gold surface, the z value. So this is the true change in z as long as dx and dy are small enough. That's a small enough change. What's a small enough change? Who knows? Small enough so that you can't tell the difference between this estimated change in z and the real change in z. But if dx, dy are, not small, a half is not small, right? A quarter is not small, 1 is not small, then dz is most likely only an estimate. Only an estimate and not equal to the true change in z on your gold surface. Right? Because this is staying on the plane, right? This is a change in z according to the linearization, the plane. Why? Because dz equals rate dx is what? Constant rate of change. Planar. So is dz equals rate times dy. That's constant rate of change, meaning staying on the plane. Staying on the plane. Dx and dy are small enough. Staying on the plane is essentially the same as being on the gold surface. Okay, very good. So we'll pick up